In this video, we used two data samples to develop a simple approach to demonstrate the analysis of variance method for hypothesis testing. We start with these two samples, A and B, each with a sample size of 4, and they represent replicate measurements of pH in each of two rivers, A and B. And we wish to test for a difference in their mean values. The factor being tested is the choice of river, and with two rivers we have two factor levels in our analysis. We start by calculating the mean and variance of both samples. So for the mean of A, it is simply the average of the values, and for the variance we use the sample variance of the data, and then we can use the same formula to calculate the similar data for river B. The variance values give a measure of the experimental uncertainty in the data, but we can get a better overall estimate of the uncertainty by calculating in H6 the average of these two variances, or the mean of sample variances, MSV, just by taking average of these two values. And now in G5 we can calculate the variance of these sample means, VSM, by taking the sample variance of these two values, and this will include the variation due to the factor difference between the two rivers, but it will also include the random uncertainties in the measurements. We must now convert these measurements into the standard mean square values that we use in an ANOVA. First of all, the mean square within samples is just the variation within the samples and without any effect due to the difference in mean values. And so mean square within is just equal to the mean of the sample variances that we have calculated in H6. The mean square between the samples will include the effect due to the differences in the mean values, and we get this by taking the variance of the sample means, but we must multiply this by the sample size n to compensate for the reduction in random uncertainties when we took the mean values of the 4 data samples. So now we see that mean square between is larger than mean square within, because mean square between includes the variation due to the difference between the mean values. And we want to test whether this difference is significant. So we will calculate the F value, which is the ratio between these values. And then if there is a large difference between the mean values of the rivers, MS between will become significantly larger than MS within, and we will have a large F value. So we need to perform a hypothesis test to test whether this F value is larger than would be expected by pure random chance, assuming there was no difference in the mean values. And to do this, we must calculate the degrees of freedom. And first of all, the degrees of freedom between the rivers is just equal to the number of factors, k minus 1. The degrees of freedom within the samples will be equal to the total number of measurements, which will be equal to the sample size multiplied by the number of factor levels, but then we must subtract from that the number of factor levels k, giving us 6 degrees of freedom. And so now we can calculate the probability that this value of f, or a larger value, occurred by chance by using the F distribution, and we will use the one-tailed distribution because we are looking for a specifically larger value of f. So we will use the upper or right hand distribution value, and we enter the F value, and then the degrees of freedom for the upper value in our ratio, which is the degrees of freedom between, and the degrees of freedom as the divisor in the ratio, the degrees of freedom within. This gives a value of 0.0520, which is just greater than the critical value of 0.05, so we do not reject the null hypothesis. There is not enough evidence to say that there is a significant difference between the two mean values, and we note that we have recorded exactly the same p-value as we did when we used the two-tailed t-value.